Welcome back. In the last lecture, we have seen the language of modal logic, where we have seen how to translate a given English language sentence appropriately into the language of modal logic, and then when we can say that a sentence is analytic, and how when it is analytic, how we can translate it into the language of modal logic. When it is a contradictory, how we translate it into the language of modal logic. These are some of the things that we have seen earlier, and we have also seen how to draw parsing trees for a given modal logical formula, and we have seen that no two formulas no two formulas can have the same syntactical structure. If they have, then they are logically identical to each other. So in this lecture we will be talking about some of the axiomatic systems that has been developed from the year 1930 to 1960s, and these are widely studied modal logical systems, and these are due to some logician or the other. We start with the minimal modal logical system K, and then we will move on to other logical systems which are considered to be extensions of K. So that means anything which is invalid in K will always be automatically be invalid in all other logical systems, because they are all considered to be extensions of K. We have all the tautologies of propositional logic, they are intact here. And then the second thing is that we have some definitions. They are like this: necessity of P, by definition it is same as it is not possible that not P is the case, and strict implication is defined in this sense: P implies Q. It is written as P implies Q, which is considered to be necessary, and it is by definition it is same as it is impossible that P is true and Q is false. And there are some other rules which is considered to be modus ponens rule, which states that it is necessary that P implies Q, it is necessary that P means it is necessary that Q. And then we have rule of necessitation, which tells us that if something is a theorem, then obviously it is necessary that alpha is the case. And these are some of the things that we already have. So now what is going to be there in our minimal modal logical system K? All these things are intact for us. The only thing which is different in the case of modal logics are we have strict implication, and then we have rules like this thing, modus ponens, and we have a rule of necessitation. So now K has this particular characteristic axiom which tells us that if P implies Q is the case, then it is necessity of P and necessity of Q. So now for any given axiomatic system, what we need to have is this thing, that is four things which you require. The first one is that we need to have some kind of parenthesis, left parenthesis and right parenthesis. This is used to read the formulas in a better way, and then you need to begin with at least two connectives. In our case we begin with only these two things. So the choice of our connectives can be any other thing. For example, Bertrand Russell and Whitehead, they have taken into consideration these two connectives, because implication can be defined in this sense in their logical system. P implies Q is defined in terms of R and negation like this, not P or Q, or P and not Q. So this needs to be ruled out. So you need to have at least two logical connectives, implies negation, or you can take even R or negation. In our case we have taken implication and negation, and then one particular modal operator you need to have. So now we are taking into consideration possibility of something P. So these are unary operators. You can very well choose necessity of P also, but you just enough to take one operator, because possibility of P can anyway be defined as this thing. It is not necessary that not P is the case. Now in addition to that, we have some propositional variables P, Q, R, S, etc. They represent some kind of sentences that it is raining or sun rises in the east, etc. all stands for some kind of atomic sentences represented by prepositional variables. So now in addition to that, this applies to any axiomatic system. If you are developing any axiomatic system, we need to ensure that we need to have these things. So now we need to know now these prepositional variables combine with the help of these logical connectives, and then we will be generating various formulas. So these prepositional variables cannot combine in whatever way we want, but it has to follow some kind of rules, and these rules are like this. If you simply write P, Q, etc., then it is considered to be a well-formed formula. All the prepositional variables are considered to be well-formed formulas. One thing which we need to mention it here, there are two symbols that we will be using it. T stands for a statement which is always true, and then bot ulta T stands for those sentences which are always considered to be false. So we use this thing especially in the prepositional logic like this. Starting from A, you end up with a contradiction. That means it has to be not A rather than A. So we have this prepositional variables. If you just write like this, it is considered to be a well-formed formula. So now these are the logical connectives that we have. P implies Q or not P is also considered to be a well-formed formula. And then if F is a well-formed formula, of course instead of P I have taken F into consideration. It does not make any big difference. So we can represent these atomic sentences as F, G's, H, etc. It is all our convenience. If F is a well-formed formula, then so as this one, possibility F is also going to be a well-formed formula. Why we require these things? We want to tell the computer that these are the things that we exhaustive things that we have. We are explicitly stating everything on the board. So now these are the things that we have, and then F implies G, P implies Q is also a well-formed formula. So now in this case I have changed it to F and G's. So now this tells us these are all formation rules. They are also called as well-formed formulas. There are rules to generate well-formed formulas. Just like in the case of natural language, cat is on the mat makes sense to us. If you say mat is on cat, something like that, also make a little bit of sense. But if you say mat, cat, on, the, etc., it does not make any sense to us. It has to combine in certain way, and then it generates some kind of meaningful formulas. Here in this context we call it well-formed formulas. So in addition to that thing, we need to have some kind of axioms, and these are all axioms in the prepositional logic. Now we take a particular kind of three axioms we take into consideration. PC1, so this is like this: F implies G implies H, and PC2. If you deny this formula and construct a tableaux tree, all the branches closes. This is a tautology. F implies G implies H, implies F implies G, implies F implies H. So this is second one, and the third formula is this thing: not G implies not F, implies F implies G. So these are the things that we have. Plus, so this is the one additional thing that we have, and this is considered to be the axiom K, which tells us that F implies G implies it is necessary that F implies it is necessary that G. Now in addition to that thing, we have some kind of rules of inference, which we have stated it already. They are like this. Suppose if F is considered to be a theorem, and then F implies G is also a theorem, then we have G is the case. So this is a modus ponens rule, and it applies to even normal modal logical system also. In the same way, if F is considered to be this is modus ponens, and this is rule of necessitation. If F implies G is already a theorem, then necessity of F implies G is also considered to be a theorem. So the list is big like this. First everything you are stating it explicitly. Now we have some definitions. So now what we are going to do with all these symbols, etc. So what we are trying to do is that using the axiomatic system K and following the rules and the axiom, we will be generating some kind of theorems. Now I will not be exhaustively proving all the theorems, but I will be considering some examples so that rest of the examples you can do it on your own. So these are some of the definitions, because F and G, since we have only implication and negation are there in our logical system, we began with implication and negation. Now we need to define conjunction, disjunction and by implication. So these are the things that you need to define. So F and G you need to define in terms of implication. So that is negation of F implies not G, and F or G you have to define in terms of implication. So that is negation of F implies G. F implies G is simply F implies G and G implies F. So these are some of the definitions, and the other definition is this one. It is not possible that F. So these are the things that we have, everything we have stated it on the board. So now using only these things, now you need to show whether a particular thing is considered to be a theorem or not. So now let us prove some of the simple theorems within the modal logical system K. Then we will see with some extensions that how other theorems can be proved in other systems. So now we are trying to prove this particular theorem. So now this I am stating it here. So this is a simple theorem which tells us this thing. Suppose if you want to prove this thing, we have something like if F implies G is a theorem. Now we need to prove necessity of F implies G is the case. So how do we prove this particular kind of thing? Suppose if F implies G is a thing, and you have to prove necessity of F implies G. So now we need to begin with something or other, some rules, etc. So now what is given to us is this one. As a first step, these steps have to be very clear and justification needs to be written on the right hand side. So this is what is given to us. This is already a theorem and this is given to us. F implies G. Step 2, we use rule of necessitation. Then using rule of necessitation, you can say that it is F implies G. Why? Because if alpha is a theorem, then by rule of necessitation it is necessity of alpha. So now 3, we need to use only those things which are listed on the board. You should not borrow any other axiom here. So now we use axiom K. K tells us that it is F and G, F implies G is necessary, implies it is F, implies it is G. So now this is K axiom. So we need to justification needs to be written on the right hand side. If you don't write the justification, then things will be difficult. Your reader will not be able to understand it. So now 2 and 3 modus ponens, you will have this thing. So now this is what you need to prove. So you started with F implies G, and we are proving a simple thing like it is necessary that F implies it is necessary that G. They are simple straightforward things. Now let us try to, I will try to show you another theorem and then we will move on to another axiomatic system, and like this you can keep on proving various theorems. So the idea here is that first you need to list out, you need to choose the logical connectives, either or negation, etc., or implication negation, etc., or you choose one particular modal operator, that is possibility, or you can even choose necessity also, and then you have the definitions, uniform substitution rules, modus ponens, rule of necessitation, and the characteristic axiom that is considered to be the most important. So now we are trying to prove one more theorem which we will try to see here, and then rest of the things you can do it on your own. So if f implies g is considered to be a theorem, the moment you need to note that when I write like this, this means is a deduction, you are deducing something. So if nothing is there on the left hand side, that means x is considered to be theorem, or it is shown to be the case. Then not g implies not f. There is some classical tautology. This is a tautology in classical logic. It is also called law of contraposition. F implies g is the case, and not g implies not f is also the case. So in that sense, so this can be written as not g implies not f. So actually it should be written like this: f implies g implies not g implies not f, and you have to apply modus ponens to one and this one, and you will get this not g implies not f. I am directly writing it here. So now 3, if not g implies not f is a theorem, then this is also considered to be a theorem. Again, rule of necessitation is the one which you have used it here. So this is what is rule of necessitation. So now fourth one, this by using k axiom, this can be simplified as this thing, that it is not g implies not f, necessity of not f implies necessity of not g implies necessity of not necessity of not f. So now this is rule of necessitation. We need to write it here. This is PL. PL means it's already a theorem in PL. This is what is given. So now these two, 3 and 4 modus ponens, this is k axiom, or it is an instance of k axiom. It is not directly k axiom, but it is an instance of k axiom. Now fifth one, 3 and 4 modus ponens, you will get not g and not f. So now this is again in the format x implies y. So this is like this, x implies y. So now from this x implies y is nothing but not y, not nothing but not x. X implies y implies not y implies not x. So now this in that sense it can be written like this. So not of not f implies not of necessity of this thing and not g. So now this is same as possibility of f, and this one, it is not necessary that not g implies, it is possible that g. So under 7 steps we could prove this particular kind of theorem. So now like this you can keep on proving it. It does not make any sense to prove any number of theorems in this classroom, but I am just giving you an idea. The idea here is that we have to use, we can use all the tautologies of classical logic, and we can use the rule of necessitation to transform it appropriately into the language of modal logic, whatever is required here, and then use modus ponens, and then ultimately you will reach your destination, that is the one which you are supposed to prove. So like this till 1960s people were logicians were constantly trying to prove theorems within the given modal logical system. So now so far we spoke about only logical system K. So now there are different other logical systems which have come into existence, and these are like this. So they are K, T, D, 4, 5 and B. So now K has this characteristic axiom, that is what you have seen here. So this includes all the tautologies etc. Together with this you have K, P implies Q, you write it as F implies G, possibility of necessity of F implies necessity of G. Now D has this characteristic axiom. So that is this thing. It is possible, it is necessary that F implies, it is possible that F. You ought to follow the traffic rules implies you are not actually following the traffic rules. It is possible that you follow the traffic rules. So this is related to deontic logic. So that's why the D system has come. And then T. T has this characteristic axiom which talks about this thing. Necessity of P, necessity of F has to, necessity of F implies F. Something which is considered to be necessary has to be actually true. Now there are other axiomatic systems that we have. So the thing is that here D was introduced first, then T has come little bit later. And these two defines this axiomatic system, D and T. There is something called as 4. 4 has this particular axiom. It is necessary that F implies that it is necessary has to be necessarily necessary. So this is what is the case. The fifth one, if something is possible that F implies that something is possible that F has to be necessary. So you might be wondering how did various logicians have come up with these various axiomatic systems. So in the process of studying various situations that you need to fit it into these logical systems, for example in this case, suppose if you translate this thing as possibility as I think that it, something is the case, or necessity as I know that P is the case. So now this is represented in the epistemic logics like this. Something is known to you, that whatever is known to you is also known to you. There are known knowns. So that is what is the case. This is also called as KK hypothesis. So something is known means it is known that it is known to you. So in the context of this thing, we require these additional characteristic axioms for given systems. This is E. There's something called E. Now we have something called as B. B has this corresponding axiom. F implies that it is possible that F has to be necessary. So these are some of the characteristic axioms with respect to various axiomatic systems, K, D, T, 4, E and B, etc. Now in the next class what we are going to do is that we will introduce Kripke semantics, and then we are going to see how Kripke has come up with the validity of a given modal logical formula just by means of some kind of relational structures. It is from 1960 onwards. There is an emphasis on the relational structures, which we call it as Kripke diagrams, or we call it as Kripke frames or Kripke models. So in the next class we will be continuing with Kripke semantics, and then where we will be talking about the meaning of a given modal logical formula.